So let's get started. My name's Paul King. I work for OCI. I live in Australia over here. If you don't know me, I do a lot of work on Groovy, but also interested in just language development as a whole. Got a few things to cover, so let's just dive right in. What is functional programming? Lots of definitions we could give. I'm going to start with a very, very simple one. A programming paradigm that emphasizes functions. Wow. Get back more, I'll come back later to what emphasizes might mean, some more detail about typical things you might want to do if you're doing programming in a functional style. But let's just get in and look at the features that Groovy just supports. So Java and Groovy support functional programming, just the fact they've got some, you could go and write methods in a static utility class and they'll have inputs and outputs, you can call them. So to some degree, even but without, even Java 1, version 1, even assembly language, at some level supports functional programming. I don't recommend you go and use assembly language for functional or object-oriented programming, but it can be done. Java 8 has lambdas, and we can leverage those in Groovy. So even just with those features alone, there's a lot of functional style things that we can do. But Groovy's, since day one, has had closures, and they give first-class support to the Groovy language. There's various things we could talk about, what first-class might mean. I'll come to some of those later. So closures are the fundamental thing that underpins a lot of the functional thing that many people will be doing if they're using Groovy for functional programming. So what is a closure? It's a function. 0 more parameters, 0 more lines of code, optionally returns a value, and so on and so forth. You're probably all familiar with it, so let's not dwell. I've got a few examples here. All of you guys, I'm sure, will be familiar with these variations here. So I'm going to skim through this material very quickly. All of this material is available on Speaker Deck and on GitHub, so you can, if you want to go back and look at any of these examples later, you can easily go and do that. So here's some examples of closures. The first one there has a type and a name. We can just call it by using the name of it's got a parameter with a type and a name. The closure itself, we're assigning to a variable. We can invoke that closure just by calling it. We use the variable name and call it as if it was like a method, and it'll return a value. We can check what that value is. The shorthand syntax that just looks like you're calling a method name there is actually a bit of syntactic sugar for calling the call method. So twice will end up being a closure object, and we're calling its call method. And there's just a bit of syntactic sugar going on there. There's other variants where we don't have any arguments. We can have arguments without any types. So they'll effectively be object as their type. If you're using them in compile static, there might be some inference going on, but if you're using it in dynamic Groovy, it'll just be object type. If you don't give a name to the parameter, there'll be a default parameter there called it. So it's like the this object. This in a class, an instance of a class, is like it inside a closure. Here I've got a method, and I can actually create what's called a method closure, and that's just a reference to that method. And so I can then treat that reference as if it was like any other closure. So I can call it and do other things with it. And now we've got higher order functions. All that means is that if we've got methods or closures here, they can take other closures as their parameters. So functions can take functions as parameters, they can return functions, and so forth. Okay, and you can see here applying something twice, I just call it and then call it again. So, okay, what else can we do? We can have default arguments. So the notation of putting equals and some value on what you might, if you've used that for methods, for one of the method parameters, you can use that with closure parameters as well. Closure arguments as well, and there's an example there. We can compose closures. There's both forward and backward composition. We can do partial application, so there's If I've got a closure that takes a certain number of parameters, I can fill some of those parameters in ahead of time, either from the left, from the right, or at a specific index. And as well as we've already seen that, so functions are first-class citizens, we've already seen that they can appear as parameters, they can appear as return types, they can appear in all of your data structures as well. So there's all the things you'd expect if you've got first-class citizen functions. Now, closures are a little bit different to what you might see in a purely functional language, and this will be one of the topics that we come back to. So in this particular example here, I've got a constant, the answer. I've got a closure here, check answer, so that's my function, and it takes a parameter guess, and it just returns a Boolean that checks whether the guess that I'm supplying equals the answer. Okay, and then I can call check answer, and if it'll return false if I pass in something that's not 42, like 21, and if I do pass in 42 or twice 21 in this case, it'll come back true. Now, is that a pure function? Well, no, it's actually referencing something outside the function. So the actual definition of the function here is the parameter, and then this bit of code inside. Guess, the first thing on the left-hand side of the equality expression that we've got there is just the parameter, so that's where that's coming from. Where's the answer coming from? We've reached outside the definition here, and we're using something from the outside. So that's a free variable, and a closure actually is executed within a context, and any free variables will be evaluated within the context that it's executed in. So that's one of the things that we'll come back to. Is that a good or bad thing? The first example, I've just got it running in a script and local variables. The same thing applies if I'm running it in a class. So in this particular example, I've got the exact same example inside a class, but I've also got logging enabled in that class. And as well as checking against this global variable, I'm also going to call a log function. And so both the log instance, log.info that I'm calling, as well as the answer global variable, the constant variable, both of those are outside the scope of the closure. So they're free variables that get filled in. So we'll come back to that. Is that an evil thing to do? Going and using a log function, going and using a constant or whatever it might be. So that's one of the topics we'll come back to. Closures are used everywhere throughout Groovy. All the libraries were built with them in mind, so there's a lot of things that you can do, and you'll be applying functional style. And whenever you ever used collect or find all or any of the standard DGM or the method extensions for collections and for various XML and SQL and so on, you'll be automatically applying various functional design patterns and functional techniques all the way through your code without even realizing it potentially. But we'll come back and look at some of those things as we go. Now, even though I've said that there's a lot of functional stuff littered throughout all the libraries, you can certainly have a style that's very imperative with Groovy. Groovy doesn't force you to do things in a functional way. It gives you the choice. So sometimes it's just worthwhile having a bit of a think about the style that you're adopting when you go and do something. So here's a little example that's just looking at style. And the details at the top and the bottom aren't all that important, but there's just happens to be a little factorial method that's defined there. I'm looking at the numbers 100 to 200, and I'm going to check whether they're both a prime and a palindrome. So a prime, we all know what a prime is, not divisible by anything else. Palindrome is just something that looks the same in the mirror, basically. Well, not quite, but it's the same forward as reverse. So if I take this here, I've got a little check for if it's a palindrome. If I take the two-string and reverse it, it should be the same as the two-string. Okay. Now what I want to do is for all the numbers between 1 and 200, check if they're both a prime and a palindrome. So that seems fairly straightforward. How do we go and do that? Let's have if we were thinking empirically to start with a sort of imperative mindset, we'd create a little for loop, walk our way through the numbers, and we might, we've got some mutable collections here that we might make use of, and we might start, as we walk through, do our little check, our prime check, do our little palindrome check, and start stashing them away into our little collector collections, and then we can print out the results when we finish. So that's a perfectly valid way of doing it. I can, with my imperative hat on, I can see a little efficiency tweak that I can do here. I kind of have this feeling in my mind that is prime might take a little bit of time to execute. It's calling this factorial special check and so on. And I know factorial can take a little while sometimes. So I'm a bit worried about the efficiency of this thing. So I'm calling is prime twice down here, once to put something in the primes collector and then once to put it in the both collector. Doesn't seem very efficient to me. So because I'm down at this low level here, I can very easily say, oh, yep, I'll stash away the result of calling my little test things here into a Boolean, and then I can just allocate the number into the appropriate collector lists that I've got based on the values of those Booleans. So that's all fine, and that all works nicely. But I do want to try to be a little bit more functional. So let's just leave aside this for the moment and think about how we might do this functionally. Well, the functional solution is actually really nice. We just go find all and supply the little test closure. So I take the nums, find all the is primes. That's nice. Then I do take all the nums and find all the is palindrome ones, and I've got those. And I didn't even need to, as far as, yes, there might be mutable collections going on underneath, but as far as my program's concerned, I haven't got these mutable collections around at this point. So I could set that thing to final and make even anyway. So there's some nice things that we'll talk about later that are apparent straight away. But the third line, I'm a little bit concerned about the efficiency thing again. I can easily write something that, and I've already shown you composing closures already, so that you could even make this look a bit nicer. I'm going to run both the checks. And as we said before, when we're doing an imperative and we're worried about this efficiency thing, which maybe it's a bit of premature optimization, I'm not sure. I can't really see at this level here how I've already gone and done the really simple answer to find the primes and find the palindromes. How am I going to do this thing for both? And at this level, there is no way to achieve better efficiency. So when you start thinking in a functional style, you've actually got to switch around how you might think about problems, and it'll turn out there is nice ways to do this and the efficiency thing isn't a concern. But you've got to have a different mindset to what you'd have in the imperative approach. So what are some of the things that we could do and still keep this nice and functional? Well, I'll just take my two collections and find the intersection of them. Okay, so that's a nice efficient way of doing this as well. I don't even need to list through the original collection again, and we've done it. I might even be concerned about, even with this solution, I'm actually iterating through the collection of numbers twice, once for is prime, once for is palindrome. So even if I wanted to do that just once, maybe it's a stream and I don't want to go and revisit the stream, we can do that as well with the inject and so on. But in this particular solution, I'm going to be down at one slightly layer below what the previous solution gave me. So functional isn't going to stop you from doing optimization. So here we're doing pretty much the same optimization that we did for the imperative case, but we're doing it inside an inject. Okay, and depending on how we go and do this, we could easily make this concurrent and so on and so forth. So there's some nice things that we might get by doing this in a functional way that might not be possible with the iterative approach. So don't be stressed if you start using functional and you think you're not going to have control of being able to do things efficiently. Yeah, you certainly can, but you might need to think about things slightly differently. I've got a section on streams, but given the length of this talk, I'm going to try to do it in about 2 or 3 minutes. So I'm going to show you a couple of streams examples as we go along. Here's that same example again, just using normal Java 8 streams. So we can just take a range closed. That'll be a stream of numbers. They happen to be primitive numbers, that particular generator. So I can make them into box numbers, which will let me pass them through the rest of this. Then I can just call .filter, and again, there's ways I could do that as a single filtering step. and then we just collect them into a list. So even using Java 8's facilities, there's nice ways to do that. And then we'll talk about some other collection mechanisms you might want to use over and above this later. So already we've seen that there's a lot of things you can do without much of a stretch of your mind from what you're probably already familiar with. So if you've been using Grails, you'll probably have been using collections in there with these kinds of find all and collects and things already. So you've probably already been starting some of this stuff. What are some of the other things that you might sort of want to consider now if we're trying to go the next level with our sort of functional guru skills? Well, there's a number of different parts to this. I could summarize it all up in that we actually want to have control of side effects. That would probably summarize. All the other three are sort of, in some sense, overlap and relate to that. I'm not saying no side effects. I'm saying control of side effects. So it's not, if I've got side effects in my program, I haven't got these pure functions that some people will tell you should have everywhere. It's not a bad thing having impure stuff there. What's the bad thing is if you don't realize you've got impure functions. So sometimes it helps to distinguish between your pure and impure and to split them into different parts. In fact, that will be a key thing for wanting to compose things in a functional way. But the biggest sin is not knowing the state of play for what any piece of code in your code base might be. So if you've got a piece of code and it's got this mishmash of side effect and non-side effect code in it, that's going to really hinder your ability to apply many of the functional techniques. And we'll see some examples of that in this next little while. Okay, so we're trying to distinguish between pure and impure, not necessarily fully rule out impure. That's going to help us, it's going to make things a lot easier to reason about, and it's going to open up a whole lot of things, the ability to do lazy evaluation, memoization, concurrency, referential integrity. We'll come and talk about all those things later on. Okay, so that's what I'm wanting to do now is kind of look at some pillars of functional programming that are going to support my ability to control side effects. So some of the pillars I want is the ability to have immutable things, potentially recursion, potentially functional data structures, and the whole concept of pure functions, knowing whether or not I've got something that's pure and whether I need to handle things in a special way, that's going to be an important thing. So we're going to come and look at these pillars in turn. Some of them I'm going to go through quickly, some I think are worth spending just a little bit of time on. Okay, so I've got two closures up there, two functions. Are they pure functions? Well, if I could have tried to be sneaky and named them in an obscure way, but because of the naming that I've got there, one's called increment and one's called increment with side effect. Hopefully you've all guessed that one of these is pure and one's not. I can test that out by doing some a little bit more of operations on either side of calling those two functions. So in the first case, I've got a integer variable that I've assigned to be 4. So it's a mutable thing. I'm going to check what its value is at later points in the program. As much as I can now, I've got an increment function. As many times I can call that as many times as I like, and I can come back later, and the integer will always be 4. I was going to say unfortunately, but when I call increment with side effect, I won't notice that particular behavior. And if you didn't realize that might be something that might happen when you do increment with side effect, then it's a bad thing. There are times when it might be appropriate to have some sort of side effect occur, but if it's going to make things more difficult to reason about if that is the case. Okay, so we're going to spell out exactly what this means. So hopefully it's obvious to you that, what this concept's all about, but I'll belabor it just a little bit to make sure it's clear. So basically, if I've got a closure, and it might be, like we saw before, calling a log function, writing stuff to a file, if it's reaching out and getting global variables, if it's sneaking around and mutating parameters that might get passed in, and various other things like that, I have to think of all the possibilities that might be going on as I'm reasoning about this. Okay, so I'm not saying it's necessarily evil, but you're going to have a much tougher job reasoning about what might be going on if you've got programs that have this sort of thing in them. So, what you'll need to do is understand the context that might be in play whenever you're running any of your functions anywhere. Okay, so are there any immutable things? Could any exceptions get thrown? Is there any sort of global state of any kind that might be in play here? If you try to minimize these kinds of functions, then you've got a much simpler job of reasoning about things. I only need to worry about the input parameters and the output parameters, and that's going to make my life a lot easier when I'm reasoning about these functions. And it's not just when I'm trying to reason about what's inside the function, it's more importantly when I'm trying to reason about big slabs of code anywhere where one of these functions might be invoked, and that is the real killer. I might have a large amount of business logic, and if I've slipped in just in one spot, anywhere in that business logic, one impure function, everything within the whole function is up for grabs as to what may or may not be happening. And we can reason about it, and we can work out whether it's a good or bad thing, but we'll have a much tougher job than if we'd eliminated it all everywhere. So should we eliminate all side effects? Well, no, we don't want to do that, because all useful output that we're going to do is going to have side effects there. So we can have computers running away forever with a huge number of calculations going on, but if we can't get something out at the end, then it's not much good to us. So we do want to have side effects. We just don't want them to affect the bulk of our code. And one of a related term that comes up that's related to purity is referential transparency. And so I'll spend, again, a little bit of time belaboring this, hopefully, because it's something that a lot of traditional Java programmers or Groovy, some Groovy programmers sort of may not cotton onto. It's a very easy concept once you get the hang of it. The idea with referential and transparency is anywhere where I've got I'll say a variable, but it's actually a value. But so if I've got def y equals, what have we got? Y equals 3. I've defined 4 references to instances up the top, and then I'm using them down here. I've assigned y equals 3. Now, referential transparency says that I can replace anywhere in my code the value on the left-hand side with the expression on the right, and vice versa. So if I've got y equals 3, what the compiler can do is just says, oh, anywhere I see a y, anywhere else in the program, I'll just put a 3 in there. Okay. If I've got x equals y plus 1, the compiler can come along and say, oh, everywhere I see x, I'll just put y plus 1. Oh, everywhere I can see y plus 1, oh, I'll just put an x. And it can arbitrarily mix and match these any sort of variable name with the expression on the right-hand side. So yeah. So let's have a look now at, with that concept in mind, let's have a look at this, what I'm asking in this particular slide here. So I've got a closure do something. I've declared those variables at the top, and I'm assigning them down below. Right in the smack bang in the middle, I'm going to call do something, and then I'm going to run an assertion that x equals z. Is that always going to execute successfully? I'm not telling you what's inside do something. Is anyone? I can't see anyone, but can anyone that got any concerns that there might this? Sorry?
Depends on what it's...
Depends. Good. So there's many things that could be inside do something where this will always execute successfully. So I've done something which is a bit, even if I do something that's a bit strange. So this is a function it'll actually be, it's got an implicit parameter it, and I've gone and actually mutated the value of that variable inside my function, which is sort of a weird thing to do. even if I go and do weird things like that, it won't affect outside, okay? Because that's a local reference inside my function, so that won't work. But as we saw with the earlier, with the increment with side effect, if I go and reach outside my function, which is what a closure can do with free variables, and I go and change y, which is one of the things that's outside, of course, things aren't going to, I cannot apply referential transparency later on, and this x equals z is going to fail, okay? And this is very obvious because you can see here I'm declaring a function and I'm going y equals something, and y, where is it? It's not declared anywhere inside my function, so I know it's a free variable, and I know I'm reaching out somewhere into the environment and modifying something. So sometimes it's really, really obvious. Other times it's a bit more subtle. So here, what I've been passed in is potentially a mutable list or something, and I'm going to call its clear function. So I'm not actually changing the reference at all, but I've gone in and invoked a mutating method on that list. And again, if I go and do that, and I've now changed it to dot size down the bottom here, the size is going to obviously change. If I feed in a list of 3 and I clear it inside my do something, it's going to change. So again, we've lost the reference transparency here. If we have something that is pure, then we can apply referential transparency. So I can go and just, if I see x plus 1 twice there, I can just go and replace the second x plus 1, I can just put an x, the second y plus 1, I can just put x there because I know that that's what I've assigned x to, right? And so then it's going to, if I go and put x there, then in fact I can then keep applying this rule, and eventually it's going to say x equals x, so I know that it's going to be true, right? So there's having referential transparency is a very, very powerful thing. And I can have a big slab of code, and anywhere if I put in one function invocation to anything that's impure, I cannot make that guarantee anymore. So that's what you need to be aware of when if you're using a functional style. Just think through all the different things that you're doing right throughout your big slab of business logic. And it applies in a sort of larger context as well. So here I've just got doing Pythagoras' theorem for the length of a triangle. With if I know 2 of the sides, I can get the third one or whatever for a right-angled triangle. Again, because if I'm applying referential transparency here, I can actually go and replace that whole thing. I don't even need the function anymore, just to replace it with the constant 5, because I can work that out at compile time. And in fact, then I can actually replace that with assert true, and I can do all that at compile time. So if I can have referential transparency, I can make my compiler do a lot of optimizations that aren't feasible in other circumstances. Okay, so I am belaboring this point. I'm going to do one more example. I'll try to do this quickly. I've just got a list of numbers, 6 numbers. I'm going to pull them off in pairs, and I'm going to calculate the power. One's the base, one's the exponent. Calculate the result of getting the power using those 2 arguments, and store that in the resulting list. And I'm going to call a power function, which I've just defined down here as base to the exponent, and I go and call that, and everything works fine. That's all good. I put on my optimizing hat, and I thought, I know that anything to the exponent of 0 is always going to be 1, so I can actually go and do a quick check here, and I'll try to make my program more efficient by doing this quick check before I go and bother doing this calculation, right? So I can return an early value. So that's all good, and that works fine. Is there any, if I look at that program and it's written in Java or Groovy, is there any subtlety there that wouldn't exist if I was writing it in something like Haskell? Anyone have a think of what they might think? There's one spot in particular that sort of stands out once you understand the differences.
The question is what gets popped first.
Correct, exactly. So the order evaluation when I'm calling a function and there's two parameters there. Does it go from left to right, or does it go from right to left? Well, Java, as does Groovy, defines it as left to right. So that's a very subtle thing that you'd think, oh, well, that's, you know, that makes sense, and that's never going to trip me up. But it can trip you up, and if you start using futures or promises or maybes and optionals, you can easily get yourself mixed up if you're not aware of some of these things. So I'm just going to show you a little example. I've heard that lazy evaluation is the way of the future. So I want to change this example and do lazy evaluation. So this example is exactly the same as it was before, but I've now got a lazy pop. And lazy pop just calls stop pop inside a closure. So I'll pass that closure into pow, and I'll change pow to, instead of just expecting the actual integer that I'm going to calculate with, here it's a closure, and when I call the closure, I get the integer that I want. So that's all good, and that all works fine. And then I think, oh, I want to put that optimization in. Premature optimization, it's a bad thing to get hung up on, but we're going to get hung up on it. So let's go and do that. Right, I've done it. So here's my example again. Everyone's confident now that if I execute this program, it's going to all work fine, or does anyone see something that might be a problem here? It's going to fail, yeah. Oops, it failed. In fact, it only gave me a list of 2 instead of 3. And I thought I was being smart. I was checking that the list had like an even number of things in it to start with, and I'm checking that it's 0 by the end and everything. And all those checks passed, but I get a list of 2 back instead of 3. What's going on here? Well, yeah, I've called exponent twice here, right? So it's going to go in lazy. It's going to do a pop here and a pop here, basically, right? So let's go fix that up. Okay, here we've fixed it up. We're going to get the exponent, store that away in E, and now I've used E twice in my expression there. This is obviously going to work, isn't it? Yes? No? What do people think? It has to work, surely. No, it's not going to work. Or I get, instead of 1825, I get 0932. Anyone know what's going on there? Yeah. So order of evaluation was left to right. Now that I'm doing it lazily, what's enforcing me to get the order right down in here? You know, it's a mutable stack that I've got here. If I start popping things off in arbitrary order, I'm not going to get them in the value that in the order that we're going to be expecting. So in order to fix this up, this is what we need to do. We need to call base first and then exponent, and now it all works fine. So we should stop here, right? We should. This is a good solution. We'll know that we've gone and found a way to make a broken way of calculating this thing work. Some other programmer is going to come along here later on and do some other optimization tweak or whatever they're going to do, and they're going to break this thing again. So what we need to do is find a different way that doesn't suffer from this problem. And it looks like I've added a whole lot of complexity here, but I haven't really done much. What I'm going to do is say, let's just leave this stack as immutable. Let's not pop the things off it. Let's just reference the items that are in it. And we can do that just by, we'll make our lazy get here, just get passed in an index, and we can just access that. I'm not going to, I've taken off my efficiency cap at the moment, and this particular collection type is going to let me easily work with this. So the nice thing about this lazy evaluator here is that I can call this at any time in any order, and it's always going to pull out, as long as I supply the correct index, it's going to pull out the correct value for me. I can call it 100 times, I can call it in any order, and it's always going to get the thing that I'm trying to calculate with. So now we've just changed it to go and bring home the point, and it's actually going to take 9 seconds, because there's 18 letters in it, half a second each. It's going to take 9 seconds to execute. If we go and just call .memwise on our closure, now it'll do automatic caching. So obviously there's 7 different characters. It's now about 3.5 seconds. That's what we expect. If we want to put some limits on that cache, we don't want the cache to grow infinitely, we can put upper and lower bounds, and then you'll have a certain number of guaranteed values in the cache, and then some garbage collectible values over and above that if you want. So you can control both ends of that range. And so we can actually have another version that's going to potentially have less impact on memory that might take 4.5 seconds on average to work this sort of thing out. And there's versions for methods as well. When memorization goes wrong, so in what this cartoon says, in 100 or 200 years' time, we're going to have really advanced problems that we've never even thought about, and we'll know, in fact, it's just clear memorization cache is going to fix your problem. So perhaps we'll have very similar problems to what we have now, or maybe not. We'll see. Okay, how am I going to do 5 pillars in 5 minutes? We'll see. Immutability. So I was using mutable lists in a lot of places in those earlier examples. There are times when that might be appropriate, but there's a lot of times when it's not. So you should consider using immutable things everywhere. And I'll show you some examples. So in the first lines of code, you won't have time to read it all, but I've got mutable lists, and I'm going to create new mutable lists, and I'm going to do mutating operations on those lists and do various calculations as I go along. There's lots of nice behavioral aspects of this second version that never mutates any list. It never uses any mutating operations. So I'm not using any functional libraries here. I'm not doing anything. So there's just by changing your style, like we saw with those go from imperative lists to using sort of more functional iteration techniques. Just by changing my style, I can actually avoid a whole lot of problems. I can improve the potential for referential integrity and so on. So it doesn't always give you wins, but this is a small step we can take. There's a lot of mutator methods that you might want to not always use, and prefer some ones that won't be mutating things. There's various things you can do. Groovy lets you do an as immutable call on collections. There's Guava and other libraries have got various immutable collections. You can use metaprogramming to stop mutating going on. So there's a lot of different things you can do. You can go and use the immutable annotation for your own domain classes to make them immutable. So there's a lot of things that you can do. So I'd encourage you to do that. But where you're going to get the next level of bang for buck is by looking at what's known as sort of functional data structures. And with functional data structures, we can have things that are mutable. We can do the immutable things, which is sort of like the Guava's immutable lists and what as immutable is going to give you. But we tend to move towards what's known as persistent collections. So over on the left-hand side, if we want to add a new character to this list, we just mutate it in place. Okay, that can be very efficient, but can have some potential issues. If we're using that, the example where I showed you the slightly modified mutating style on a couple of slides back, then we don't ever touch the 2-character version of this list, but we create a brand new 3-character. So we copy the whole thing across and create a 3-character, and then we use that from then on. What the persistent collection version does, and there are lines joining all those boxes, but I suspect you won't be able to see any of those, but they're actually a list of connected boxes here. We try to reuse the data structures of existing lists in new lists, and sometimes that works really well, and other times there can be issues. So let's have a look at some of the kinds of things that can go on here. I've got a pets object, and it's got 3 things in it. And I want to add I want to buy a fish, and I'm going to add that to it. It turns out I can actually use this persistent idea, and I can get basically 2 collections for the price of 1. So anybody who's still referring to the old version of my list will have a reference to pets, And they'll just see a list of 3 things. The new version, when I went and added something to it, it just appended a new thing on the list, created a new reference, and that new reference pointed off to the old reference. So anyone who's looking at new pets will see 4. And that's all really nice. What happens now when I go and want to remove, I want to sell the horse over here. I want to sell the horse now. What do I need to do? I actually need to do a whole lot of copy operations. Now I can have some people looking at the 3 version of the list, some people looking at the 4 version of the list, and some looking at a brand new 3 version of the list, and I'll have copied things across. Because everything's immutable all the way along, a direct copy is easy to do. But you can see here, when I start to moving over to these persistent collections, some operations are going to be really, really easy to do, some are going to be expensive. And the same things happen with the trees. So we can have balanced trees and all sorts of things. The thing is, you move over to this style, you need to be aware that if I'm going to do certain kinds of operations on these data structures, some will be really performant, some won't. Some will be horribly performant. The good news is that other people have gone and worked out how to do efficient versions of all these sorts of things. So you can go get a red-black tree, a finger tree, all sorts of different data structures that have been optimized to work well in certain scenarios. So there's good news if you want to use these things. Okay, here we're balancing a red-black tree, but we're changing the requirements as we go. But anyway, I'm going to skip this stream section altogether. There's lots of places where lazy evaluation is already occurring in Groovy. You've probably already used some of them. You can use singleton and lazy. There's a bunch of other libraries that you can be using over and above what Java gives you. We'll skip over those and move on to there's 2 more points. 1 minute each. This is going to be interesting. Actually, I've got 3 more points. Recursion, it's just applying the divide and conquer strategy. So I don't know how to solve factorial n, but I do know that it's n times a smaller problem, and we just go and apply that, and that solves our problem. There's just one little trick that you have to do in Groovy is if you declare factorial and you try to reference it inside itself as in a closure, it'll say, I don't know, this is something you haven't defined yet, and I won't let you do that. There's just a couple little tricks you can do. I can just declare factorial and then I can define it in terms of itself because it knows about the reference, or I can just use the call method as another little trick. And that works fine, but it suffers stack overflow. And what we tend to do is actually make the program uglier and harder to read and harder to maintain, but put it into something that's known as tail call recursive form, and that's what we can do here, and there's a couple of different ways I could do it, but it's still subject to stack overflow. So what we'd use is a thing called trampolining. And what trampolining does is it creates a wrapped version of our recursion that if it ever gets an intermediate result that is itself a trampoline version, it just keeps calling itself. So it does an infinite loop until it ends up with something that's not a trampolined result. And if I just call trampoline like that, I'm not going to get what I expect, and I'm going to cut a long story short. You do a second dot trampoline, and you'll now get something that's going to, whenever you call it, whether it ever goes into the trampoline thing or not, it's going to give you a result back. And so that's the kind of thing that you would want to do to optimize a recursive call, and you can do mutual recursive calls as well using that same technique. Same thing for available on methods as well, as long as they're in the tail recursive form. And tail recursion is its own reward. There we go. What I've got now is 2 examples. And each one deserves about a half an hour each, but we'll see how we go. Here I've got a problem where I've got a whole big slab of text, and I want to count the number of words. And I've got available to me large numbers of processes, and I want to solve the problem. When I first look at the problem, it looks like I can't solve it easily because when I've got my list here, say that I'm halfway through, say this chunk here that starts with the I and ends with the N here, the third chunk, if I give that to a processor, how is it going to count the words? Because it doesn't know whether it's at the start of a word as the first character it's been given or not, until it gets the result of the previous one, and the previous one can tell it, yeah, you're at a word boundary or you're not. So when you first look at this problem, it looks like it's a serialized problem and there's no way to make it concurrent. But what we can do is actually twist the problem around, and this is something that you'd want to do as a functional style. Twist it around slightly. Sorry? Time to stop. So we're going to twist that problem around, and we're going to keep track of things called chunks and segments. And basically, what I can do is count the words through the bulk of my chunk, but remember what's happening at either end. And then I can create a combination operator that says what to do if I've got two of these things. So I can just, if I've got two chunks that are side by side, I add up all the words on one, add up all the words on another, and then I combine the leftovers that we've remembered. And that's what we need to do. 2 minutes, excellent. And so that's what we do in this particular case, and you can go and have a look at this thing, and it turns out that what I've actually got is I'm creating a data structure, and I've got some combine operators in this data structure, and I've got what's called a zero element, which is what to do on the ends. So when I'm adding these things together, what happens if I'm at the end? Because I don't know that I'm at the end necessarily. So I need to have what's called a zero term, and I need to have a way of combining these terms. And as long as I go and define that, it turns out that I can just automatically, concurrently now, calculate that problem using a whole range of different techniques. And the slides will show you how to do it with data flow and parallel arrays and fork joins and so on. This is what's called a monoid. And as long as you can go and define, you can actually apply this on a whole range of problems that you might not think that you can apply. Okay. The final problem I've got, everyone knows the most famous monad in the world. It's Monad Lisa, of course. There's just a quick monad example here. And I've actually simplified this down to try to get the idea across. And I can actually use what's called an applicative functor to solve this problem. So I don't actually need the monadic thing just yet. But let's have a quick look at what's going on here. I've got a sine function and a cube function that just work on numbers. And I can compose them, that all works well. I decide that I want to add debugging. So I now change them. Now I've oversimplified it to actually make it back into a pure function, which kind of defeats the purpose of what I'm doing, but let's just go along with this for now. What I'm going to do is actually return a tuple. I'm going to return the actual math function and also my log message. And I can do that for sine, cos, and sine and cube here. But if I try to now use my compose operator, it just breaks. Obviously, one's expecting a number to come in, and the other one's spitting out a number plus the log message, a tuple. And that's going to break. We can go and hand write a compose debuggable that takes that into account, and that's all fine. But instead of that, what I can do is define a generic bind function that takes one of these function that takes a number and returns the tuple, and actually turns it into a function that takes the tuple and returns a tuple. And now I can actually go back and use my normal compose here. Then I can say, well, that's all good, but it's a bit ugly at the ends of this thing because I'm expecting to pass in a number, and I actually have to pass now in a number and a string to kick this thing off. So I can define a unit function that lets me poke things in the end. That's all well and good. Then I still don't like having to operate with the two things, so I can create a lift method. And to cut a long story short, what I can do by creating generic versions of these, it'll be called bind or flat map, and there's various names for these things. By creating these different functions, I can now go use the original compose methods that I wrote for closures, the original mathematical functions, but I can now combine things that are doing debugging, or that are doing null checking, or that are doing manipulating state, or a whole range of other things, and I can get code reuse across a whole bunch of these different things. Okay, you can go get the source code for that and have a bit of a ponder at a later date if you want to know more about that. A bunch of links there. You can go and have a look at. There's a thing called Functional Groovy that's got some good stuff. There's a bunch of people, including some people in the audience here, who've gone and written some good documentation on doing functional programming with Groovy, so I recommend you to go and have a look at those. Okay, I think I'm out of time. If you've got any questions, come and see me afterwards. Thank you.